Okay, so good evening everyone. Thank you for staying until so late. So I'm Eunice and today I'll be talking about the effects of low light on the optimal temperature for productivity in Halophila ovalis. So as we know very well, seagrasses are extremely important habitats as they provide a range of ecosystem services, and unfortunately 29% of the global seagrass meadows had disappeared worldwide over the past centuries, and major threats include reduction in underwater irradiance levels probably due to coastal development works as well as rising sea surface temperatures associated with climate change. Past studies have shown that seagrasses are able to cope with short-term acute reduction in light level, and this is done through various morphological and physiological changes, which includes shoot density, leaf size, and chlorophyll content. Studies have also shown that seagrasses exposed to warmer waters tend to have higher compensation irradiance level as a way to compensate for the higher respiration rates present in warmer waters. However, there has been limited research attention given to investigating the effects of reduced light level on the thermal optimum of seagrass productivity, and most research in these areas tends to focus mainly on terrestrial angiosperm species. So thus, my study seeks to actually achieve these three objectives. So firstly, the effects of prolonged in-situ shading on the thermal optimum of productivity in Halophila ovalis. Secondly, the effects of shading on seagrass morphology and chlorophyll. And lastly, the post-shading responses of H ovalis for any signs of seagrass recovery following the removal of the shading treatments. So in my study, the thermal optimal of seagrass productivity actually consisted of the optimal temperature of photosynthesis, which is T-op, maximum photosynthetic rate at T-op, which is P-max, and the temperature where photosynthesis stopped, which is T-max. So as you can see on this graph here, this is the temperature-dependent response of photosynthetic rates. So as temperature increases rapidly, the photosynthetic rate will increase, as temperature increases, the photosynthetic rate will increase rapidly until it reaches the highest here, Pmax, and this is attained at the optimal temperature of photosynthesis. And for temperatures greater than the optimal temperature, the photosynthetic rate will drop. So at the rate where it's 0 is the Tmax. So actually for this study, it was conducted between August 2017 to January this year, and it was done at the H ovalis meadow at Chek Jawa, which I think some of you will be visiting tomorrow. So it's actually located on Pulau Ubin, which is an offshore island located on northeast of Singapore mainland. So H ovalis was chosen as the study species as it is known to respond quite quickly to environmental changes due to their high turnover rate, as well as it being one of the most common species in Singapore. So to bring about the shading treatments, we actually subjected the seagrass meadows to shading treatments for 12 weeks via the deployment of self-assembled shading frames you can see here. So to bring about the different treatments, we use different types of nets and different number of shade nets. So we have high shade, which is 68% shading, low shade, which is 50% shading, and control, which is 0% shading. So for each treatment, I had 4 replicates each, and they were arranged in a 4x3 arrangement. So actually this is the actual field site. It's very nice, right? So after 12 weeks of shading, we removed the shade nets, and recovery was monitored. Any signs of recovery was monitored for another 8 weeks. So this one is known as the post-shading phase. So across both the shading and post-shading phases, we actually measured the shoot density, leaf length, and leaf width every 4 weeks. And from the leaf length and leaf width, we calculated the leaf surface area. So actually measurements was done within a quadrat placed in the middle of each shading frame. And outside of each frame, we actually collected seagrass samples for chlorophyll extraction as well as for the incubation experiments. So this incubation experiment was actually used to determine the respiration and the photosynthetic rates of the seagrass. So for each experimental plot, we separated a pair of leaves from the rhizomes and we placed them in separate incubation jars. The incubation jars was then placed in the incubation tank, which received cooled or heated water pumped from the water bath into here. So the jars were then subjected to incubation treatments that ranged from 22 to 42 degrees Celsius, and at each temperature, the leaves and rhizomes were incubated in the dark to determine the dark respiration rates. The leaves also incubated under their respective in-situ shading treatments under their saturating irradiance to determine their net above ground photosynthetic rates. So actually dissolved oxygen levels was monitored to come up with all these different rates. So after that, we actually use this Yen and Han model, which is actually based on this temperature-dependent response of photosynthesis, to fit to the photosynthesis versus temperature data to come up with the following estimates. So the optimal temperature of photosynthesis, the maximum photosynthetic rate, and the temperature where photosynthesis stops. So as you may recall, these are the parameters of the thermal optimum of seagrass productivity. So in addition, we also calculated the photosynthesis to respiration ratio at the average in-situ temperature of 30 degrees Celsius. So we use this formula here, and we feed in data from the 30 degrees Celsius incubation experiment. So for P is to R ratio greater than 1, it represents a photosynthetic surplus where photosynthetic rate is greater than respiration rate. So moving on to results and discussion, for the objective on the effects of shading on seagrass morphology and chlorophyll, we found that during the shading phase, which is represented by the darker gray area, high and low shade actually experience a significantly lower shoot density as compared to the control. So these are the high and low shade treatments. So a possible reason for this is because by reducing their shoot density, it helps to minimize cell shading and actually allows more light to reach shoots that are smaller or shorter. Moving on to the post-shading phase, we found that from week 12 to 18, which is here, this gray portion here, there was a significant increase in shoot density experienced by the high shade treatment. And this could be a possible sign of seagrass recovery. However, during weeks 18 and 20, we noticed that high and low shade actually experienced a drop in the shoot density, and this could be due to a drop in the natural in-situ irradiance level. However, this change was not observed in the control. As you notice here, it's actually quite similar. There was no significant change here. And the possible reason for this difference in response could be due to the different light histories experienced by seagrasses growing under the low shade, high shade, and control treatment. So actually, studies have found that seagrasses growing in chronically low light environments have lower resilience to further reduction in light levels. So this could actually affect their response to further reduction in light levels. So moving on to leaf surface area, during the shading phase, we noticed that the high shade, which is this red line here, was actually smaller than the control treatment. So this could be because leaf respiration tend to be about 7 times higher than the rhizome root respiration, and leaf might be a huge respiratory burden for the seagrasses in the presence of lower light level. Thus, reducing leaf size might be a way to conserve the limited carbon resources. So moving to the post-shading phase, we noticed that across all treatments, there was significant increase in the leaf size, and this could be a possible sign of seagrass recovery. So for chlorophyll level, we didn't notice any significant shade effect, and this could be because unlike other angiosperm species, for seagrass chlorophyll pigments, they tend to be found only in the leaf epidermis. So as a result, they are unable to spread out, and this could result in the chlorophyll pigment shading each other. So actually this gives rise to this strong package effect in which there's a non-linear relationship between the light absorption efficiencies of chlorophyll pigments and the chlorophyll densities present in the leaf cell. So for the objective on the effective of in-situ shading on the thermal optimum of productivity, we found that there was no significant shade effects for the various parameters of thermal optimal. And actually, as you notice on this graph here, the range was about 25 to about 30 degrees Celsius, and actually this overlaps with the range proposed by, the optimal temperature range proposed by an earlier study. So in addition, we also noticed that for the P to R ratio, there was no significant shade effects, and in fact, most of the weeks actually experienced a P to R ratio greater than 1, which means a photosynthetic surplus. So this could be because Halophila species in general have a relatively low minimum light requirements. In particular for H. ovalis, they require about 40 micromole, which my treatment, as you can see here, is actually way above. So probably my shading treatment might not have been strong enough to bring about any obvious physiological changes. Then in addition, Halophila ovalis has a relatively small biomass, so this kind of lower their respiratory demand, and thus even under reduced light level, they're still able to synthesize enough carbon to experience a photosynthetic surplus. So during the post-shading phase, similarly, there was no significant shade effect for the various parameters of thermal optimal, but we noticed that for the P to R ratio, high shade actually experienced a significantly smaller value as compared to control. So as I stated earlier, this could be because this could be because of the differing light histories experienced by seagrasses growing under the high shade, low shade, and control treatment. And this could mean that seagrasses under high shade might be more sensitive to the reduction in light levels during the post-shading phase as compared to the seagrasses under the control, which might have affected their photosynthetic rate. So in conclusion, my studies found that shading had significant effect on the seagrass shoot density as well as the leaf size, but there was no significant shade effect on the seagrass physiological traits such as the thermal optimum as well as the chlorophyll. And during the recovery post-shading phase, we found that recovery was more evident through the visual assessment of various morphological traits. And this could mean that shading had greater effect or more obvious effects on seagrass morphology than seagrass physiology. So perhaps future studies could consider using longer shading duration as well as higher shading percentage to bring about probably stronger shading effects on the seagrass physiology and morphology, as well as to consider using slower growing or more climax species instead of a fast growing species like Halophila ovalis. Thank you.
Thank you, Eunice. Anyone question? Yes.
Thank you very much. It's very interesting work. I have a question about the experimental setup. Did you measure the intensity of the light using the daytime? Because if I right, you just put the shading net on top of the box, right? But because during the daytime, we have the direction of the light will come from the side.
Yeah.
So I'm not sure if it's really shading, high shading, or low shading as you propose.
Yeah.
Did you measure?
Yeah, we actually measured. So actually what we did was we put the light logger. So it's like we have the central quadrant and we put the light logger outside the central quadrant. So some of the edges might have more light, but we try to take our samples closer to the center. Yeah.
Okay.
Yeah.
Okay. Yeah. Thank you.
Okay.
Thank you.
All right, then let's join us in thanking Eunice for her excellent talk.